problem. So last time we had our the I give you the brief, not brief, like the beginning part of the algorithm, like how the algorithm will start for in the first iteration. So this time we can start with a pseudocode of rank maximal matching. So have you gone over that algorithm from the paper? Hello. Okay, okay, no worries. Okay, so we can start. So I think it's visible, right? So what we had done was we had this G1, G2, Gi, and G. So we had this graph called G1, G2 dot Gr. And do you remember what is this Gis? I mean G1, G2, Gr. So here Gi was A union P, comma. No, 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 not just rank I edges. All the edges of rank less or equal to I. Yeah. Yeah. So these were the edges. Okay, so this is Gi. So what was the algorithm? So if we check here in the pseudocode, so we started with G1. G1 was A union P, comma U1, and we said that G1 prime is equal to G1. Okay. Now what we did, we found a maximum matching M1 of G prime 1. Then what we did, this is like a for loop from 3 to 8. First we computed first we partitioned the vertices of G prime I into EI, OI and UG prime I. This means the even vertices of G prime I, this is odd and this is unreachable. Okay, just one more thing. So are you comfortable with pseudocodes? I mean, you have seen this kind of this. Okay, okay. So it's like a it's okay, okay, great. So this is like a for loop here. Inside the for loop, what you are doing for I equal to 1 to r, you are first partitioning this G prime I into even, odd, and unreachable because you already have this graph Mi of G prime I. Because you have this graph Mi of G prime I. Then what you are doing, you are deleting all the edges Ej such that j is greater than I, strictly greater than I, that is I plus 1 onwards, for incident to the vertices of O of G prime I and U of G prime I. So basically you are finding all the even, odd, or unreachable vertices of G prime I. Then what you are doing, incident to all, you are taking all the odd and unreachable vertices of G prime I and you are removing the edges of higher rank. That means edges of rank J where J is strictly greater than I. That means J cannot be I. So J can be from I plus 1 to R. Okay, and after that what you are doing, you are removing all the OO and OU edges from G prime I. And after you finish this, then what you are doing, you are adding all the edges of rank I plus 1 to the graph that is still present in the graph. And you call that resulting graph as G prime I plus 1. And after that, finally, what you are doing is you are computing a maximum matching Mi plus 1 of G prime I plus 1 by augmenting the current matching Mi. So you remember why we did do it by just augmenting but not just finding any maximum matching of G prime I plus 1, because we have seen one example before, I think. Here in this example we have seen that if we don't find the maximum matching of G prime 2 using by augmenting the old matching, then we could have such a matching where we only have two rank 2 edges matched, whereas it is not a but it is not a rank maximal matching. Okay, so this is the pseudocode of the algorithm. So is there any question about this? So this basically we have done it for the rank 1 and rank 2, but now it is basically a generalized version of that. So do you have any questions? Then you can tell me, I can explain that part. Yeah. line 5 and 6 don't affect the edges of mi. Yeah, because m what sorry. Yeah, bigger edge. 6 cannot affect because they are in the edges of type oo and ou cannot be part of a maximum matching. That's from the Galley electron decomposition. That's why these two edges doesn't remove anything that belongs to mi. Okay, so this is the main algorithm. So any questions, anyone else? So this we are deleting from G, the 5 we are deleting from G because these are the higher rank edges, so it's not present in G prime I. That's why we are removing it from G. Okay, and this we are removing from G prime I. Yeah. Okay. Okay, so you can think it like this. You have think in terms of like this. You have some edges, and each edge belongs to one of the R buckets, like R sets, and basically you are removing the edges from there. Okay, so basically you are you have you have removed the edges of rank J from that particular set EJ. It's like that. Okay. Any question about the algorithm? After this we are going to see the correctness of this algorithm, that why this algorithm basically gives us a rank maximal matching. Shall we proceed or do you have any questions, anyone? Okay, great. So next we are going to see why it actually gives us a rank maximal matching. Okay, so the correctness has like two lemmas and a theorem. So one main theorem and two lemmas to support that theorem. Okay, so I'll start with that. So the first lemma is, suppose maybe that every rank. So what is the first lemma? Lemma 1. It says that suppose that every rank maximal matching of Gi is a maximum matching in G prime I. Okay, if we are as we assume that, then we prove that every rank maximal matching of Gi plus 1 will be is contained in G prime I plus 1. Okay, so what we are going to show is, if we remove the edges of the edges that we are removing during the ith iteration will not be. Yeah. How? uh, basically so basically what I'm going to show that if this happens, then in our algorithm, I mean this will be of course true, but what is your approach then? I mean, how you are going? Yeah. So basically now what we are doing, we gave you an algorithm right here, but we don't know if this gives us a rank maximal matching on each iteration or not. So now we are going to prove in it this algorithm indeed gives you a rank maximal matching. So you don't know that by removing those edges you will indeed get a rank maximal matching, right? You still don't know. Yeah. So basically we'll show that our algorithm is like correct. So by so this is just a lemma to prove the main theorem. This is not a main theorem. So here we are assuming that in the ith iteration, every rank maximal matching is a maximum matching of g prime I plus 1. Then we will show that every rank maximal matching will be contained in g prime I plus 1. Okay. So how will so what we have to show now? So we have to show that the edges that we are deleting in the ith iteration are not part of any rank maximal matching, like the edges of higher rank or something that we have deleted, or OI and OI and so what are the edges that we have deleted? We have deleted the edges incident to OI and EY of higher rank. Okay, what edges have we deleted? What edges have we deleted during iteration I? Yeah, yeah, sure. Yeah. No, no, this is like a this is like a generalized version of the. I mean, okay, this is not the theorem. The theorem will come later. This is just a lemma that we are that is needed to prove the theorem. Okay. Yeah, yeah. The theorem. So we'll have like two lemmas, and after that we'll have the theorem. So now what we are saying that what are the edges that we delete during the iteration I? So one is the edges incident to and to y and ui of rank j strictly greater than I. So this one we do, and two is y and ui edges. So our claim is that the edges that we are deleting will not be part of any rank maximal matching. Okay, and in that case, every rank maximal matching will be contained inside this g prime I plus 1. Okay, is the proof approach of the proof clear? So we will prove that the edges that we are deleting during the I plus 1th iteration or ith iteration, the edges in the higher ranked edges incident to OI and EY, and also the OI and OI edges will not be part of any rank maximal matching of G I plus 1. Okay, so how to prove that? Okay, so first let so we'll start with a rank maximal matching of mi plus 1 be a. Okay, let's say that mi plus 1 be a rank maximal matching of gi plus 1. We will prove that it belongs to the mi plus 1 is a subset of g prime, is a maximum matching of g prime I plus 1. Okay, that is our goal to prove. Um, It's a subset of G prime. It's contained in. Okay, we don't. Okay, we don't need to prove it is a maximum, but it will indeed be maximum. But we don't need to prove it now. We just want to prove it is contained. Okay, so we start. Okay, so one thing before I go. So you understand the meaning of mi plus 1 be a rank maximal matching of a gi plus 1. So I'm saying if we just take the subset of G where we don't take any edges over the rank I plus 1. So we just take only the edges of rank I plus 1 or less. Then mi plus 1 is a rank maximal matching of that particular graph. Okay. Okay. So mi plus 1 is a rank maximal matching of Gi plus 1. Then uh, we claim that mi which let's define that mi may be mi plus 1 intersection ej. Okay, let me write it below. Yes, the recording is on. uh, mm, yeah, so we claim that mi, let's define mi as another matching mi plus 1 intersection e of less or equal to I. So basically we are taking the matching mi plus 1 and we are removing all the edges of rank I plus 1 from that matching, and we are taking remaining edges and we define it that matching as mi. We claim that this is a rank maximal matching of gi. Can you see that why it is true? E- exactly. And then yeah, is another signature that is basically okay. So let's say the signature of mi plus 1 is r1 r2 ri plus 1. Okay, now signature of mi is r1 r2 ri. Yeah, after that. Mhm. Exactly. So basically, if exactly you're correct. So if mi is not a rank maximality, you're absolutely correct. Mi is not a RMM of GI. Then there exists m prime I, uh, which has a better signature than mi in GI. Now we can note that m prime I is also a matching in gi plus 1. Also note that m prime I is a matching in gi plus 1. Why? Because gi plus 1 is like a superset of gi. Gi is basically a subset of gi plus 1. That's why m prime I is also matching in gi plus 1. But then the signature of m prime I is strictly better than mi I plus 1, which is a contradiction. Is it clear why it is not, why mi is a rank maximal? So what we have done, why mi is a rank maximal matching of gi? So if it is not a rank maximal matching of gi, then we have a matching m prime I, which has a better signature than mi, and that means there is a, so if we say that signature of m prime I is like this, s1 s2 dot 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 si, then there exists some sj less than si, such that sj is strictly better than rj. And now if we consider this m prime I matching in gi plus 1, then m prime I is a matching in gi plus 1, because gi plus 1 is a superset of a supergraph of gi, and then m prime I will have a better signature than mi plus 1, and which will be a contradiction, because mi plus 1 is a rank maximal matching that we have assumed. Okay, so from here we can say that mi is a rank maximal matching of gi. Now if we have this, then what we have assumed, what is our assumption here? Every rank maximal matching of gi is a maximum matching of g prime I. So from here we can say that mi is a maximum matching of g prime I. Clear? Now all the vertices, then what is, if mi is a maximum matching of g prime I, then what we can claim? We can claim that all the vertices which are oi or of type ey are matched with an edge of rank I or less. Then all the vertices of type oi and ui matched in mi. Okay, if it happens, then those vertices cannot have any edge of rank I plus 1 incident to it in mi plus 1. Then those vertices yeah, yeah, of a, when we found a maximum matching in g prime I, then we found those oi and ui. Yeah, no, it's a different maximum matching, but we have seen that, exactly, it doesn't depend on the maximum matching, that's why, sorry. We have proved that this partition of odd, even, and unreachable, it doesn't depend on the maximum matching. That's why we can take. That's why we can take any maximum matching. And since we have proved that mi is a maximum matching of g prime I, then all the odd and unreachable vertices can be found by, with respect to mi also. And if you check the Galois-Edmonds decomposition theorem, then you will see that all the vertices that are oi or ui, odd or unreachable, will be matched by an will be matched by an matched edge, will be incident to a matched edge, because if it is a free vertex, then it will be even. So all the vertices which are oi and ui, of type oi and ui, will be matched by some edge in mi, right? Now what was our mi plus 1? If you remember, was mi was basically mi plus 1 intersection of this edges of less or equal I or less. So those oi and ui type vertices cannot be incident to a rank I plus 1 edge in mi plus 1, right? Or be incident to a edge of sorry, I could not hear. Yeah, incident to an edge of rank I plus 1 in mi plus 1. Yeah, yeah, because rank I, exactly. Yeah, and if it has a had a edge of rank I plus 1, then I mean after you compute mi, those vertices will be unmatched, right? Yeah, so that's why, yeah, even. Yeah, so that's why we said we can claim that those vertices will not be cannot be matched by an edge of rank I plus 1 in mi plus 1. So this one part is done, that if we remove the higher rank edges incident to oi and ui, then it is not making any problem for us, because those vertices cannot be matched to an edge of rank I plus 1 or more. Okay, so the second thing that we need to prove is, if we remove the edges of type OI, OI and OI, UI, then that will also not be a problem. Those edges also cannot be matched in MI plus 1. Okay, so the next thing is the edges of type OI, OI and OI, UI can't be matched in MI plus 1. So this is the second thing we need to prove. This is also clear. This is also very obvious. Can anyone tell me why it is true? Observe the matching mi. Can there be an edge of type oi, ui and or oi, ui in mi? No, right? No, not that way. So let's do that in this way. Suppose there exists an matched edge of type oi, oi in mi plus 1, right? Then that edge belongs to mi also, because of the definition of mi, because y edge, this edge, both endpoint is this edge will be is of type is of rank I, so this edge will be present in the graph. So this edge, I, yeah, because y when we computed this y edge, we computed in g prime I, so it is of rank I or less. Okay, yeah, so now that is also belongs to mi, but mi in mi this edge cannot be matched, but in mi this edge can't be matched because mi is a maximum matching, so this oi edge cannot be matched in mi. That's why this y edge cannot be matched in mi plus 1 2. Then we have a contradiction, we can write it. Okay, so how you are doing it? So I will repeat it one more time. So the edges of type OI, OI and OI, EY cannot be matched in MI plus 1. So let's suppose that, assume that there is an edge of type OI, OI which is matched in MI plus 1. Then that edge, so if we remove the edges of rank I plus 1 from the matching, then that edge will also be matched in MI, because if there this y edge of because if this edge was of rank greater than equal to I plus 1, then that edge will be removed, because both of its one of its endpoint is basically of odd. So in that regard, this edge will be removed. So since this edge was not removed, that means this edge is also present in MI, and that means the rank of this edge is less or equal to I. So rank of this particular edge, rank of this edge is less or equal to I. And if it happens, then this edge all must belong to MI also, because MI is basically MI plus 1, and we are removing all the edges of rank I plus 1 from MI plus 1. But if this edge is matched in MI, then MI cannot be a maximum matching, because a maximum matching cannot have any edge of type OI or OI, and that's why we have a contradiction. Is this clear, or any question about this? So I'll just shorten this. Yeah. So now I think it will be visible more. Uh, so any question about this lemma? Yeah. So what was the statement was basically, we assume that every rank maximal matching of GI is a maximum matching of G prime I. Then we claim that we want to prove that every rank maximal matching of G I plus 1 will be contained in G prime I plus 1. So we assume that every rank maximal matching of GI is a maximum matching of G prime I. That means every rank maximal matching of GI is contained in G prime I. Then we want to prove that every rank maximal matching of GI plus 1, the next iteration, will also be contained in G prime I plus 1. So how we proved it? We proved it by saying that the edges that we are removing during the ith iteration will not be part of any rank maximal matching in GI plus 1. Okay, so how do we do that? We first say that we check what are the edges that we are removing during iteration I. So the edges that we are removing are of type odd and unreachable incident to so the edges incident to odd and unreachable vertices of rank J, which is strictly greater than I. And the second type of edges that we are removing is OI and OI type of edges. So first we prove that if we remove any edge of rank J which is strictly greater than I incident to OI and EY, then those edges cannot be part of any rank maximal matching of GI plus 1. Okay, so how do we prove that? We first we start with a rank maximal matching MI plus 1 of GI plus 1. Then we define MI, which is MI plus 1 intersection all the edges of rank less or equal to I. That means basically we are removing the edges of rank I plus 1 from the matching MI, and the MI plus sorry, we are removing all the edges of rank I plus 1 from the matching MI plus 1 and denoting it as MI. And we claim that this will be a rank maximal matching of GI, and also this will be and by our assumption, since it is a rank maximal matching of GI, by our assumption that every rank maximal matching of GI is a maximum matching of G prime I, we can also claim that this matching MI is a maximum matching of G prime I. And after that, then we know from Gala-Edmonds decomposition that all the vertices of type OI and EY will be matched in MI. And then and that means those vertices cannot be matched to an edge of rank I plus 1. because those edges, those vertices are already matched with an edge of rank less or equal to I, because they are already matched in mi. And that basically proves the first point, that the edges incident to OI and EY of rank I plus 1 cannot be matched in any rank maximal matching. The second thing is that the edges of type OI and OI cannot be matched in MI plus 1. So we prove it for OI and for OI it will be similar. Suppose that there exists a matched edge of type OI in MI plus 1, then that edge also belongs to MI, because that edge will have the rank of less or equal to I. And if it happens, then in MI also that edge will also be matched. And we know that in a maximum matching, an edge of type OI cannot be matched. And that means it is a contradiction that MI is a maximum matching. So this basically completes the proof. Any question about this? This one? Okay, so first of all, you remember how we have defined MI? Let me write it with different color. So MI is basically MI plus 1 intersection edges of rank of less than I. So this is MI, right? And in MI we have proved that those vertices of type OI and UI will be matched. So that means those vertices will be matched by an edge of rank less than or equal to I. So those vertices cannot be matched with a edge of rank I plus 1 in MI plus 1. That is the point. So where do you have the doubt? Okay, so think it is in this way, that MI is basically a matching that we are getting by removing some edges of mi plus 1. So mi is not all the edges that are present in mi are also present in mi plus 1. Only thing is that mi plus 1 have some more edges, that is of rank I plus 1. That's the only thing. And now if mi oi the vertices of type oi and ui are matched in mi, that means those matched edges will be present in mi plus 1 too. And that means those matched edges will have rank of less or equal, also those matched edges will also have rank of less or equal to I, because they are also present in mi. So that means the vertices incident with of odd and unreachable type, they cannot have any they are matched with an edge of rank I or less, so they cannot be matched with an edge of rank I plus 1. That's the point. Is it okay? So maybe you can go over this part and you can write me. I mean, I can explain it to if you have doubt after reading it. Okay. So in the next part, so is it clear to everybody else or any doubt? Okay. So if it is fine, then we can have the next lemma. So the next lemma says, for every j greater than I, the number of edges of rank at most I is the same in mi and mj. So mi and mj are the matching that we got from our algorithm in ith and jth iteration, and we claim that in both mi and mj, the ages of rank less at most I is will be the same. Okay, so how to prove this? So one thing is that mj is obtained by augmenting a, yeah, yeah. So mj is basically obtained by augmenting a maximum matching mi of gi, right? So mi is a maximum matching of mi is a matching in g prime I, and mj is a maximum matching in g prime j. So mi is a max matching of g prime y, max, and this is a max matching of g prime j. Yeah, but so here I want to say is, okay, let me write it. So after ith iteration we get I plus 1, but continuous augmentation I mean. So yeah, one step. So maybe I should write in a continuous augmentation. uh, mj after several augmentation. So one thing you can notice about augmentation is, suppose this is a matching. So here we can see that u and v are the free vertices and rest of the vertices are matched vertices. And if you augment this particular augmenting path, then we can see that every vertex gets matched. That means the vertices which were matched in the previous iteration, before we have augmented, they also remain matched. Is it clear? So when you have a matching and you apply an augmenting path, then the vertices which were matched before the augmentation will remain matched after the augmentation. Okay, so let me write it down. So we have a claim, small claim. Let M be a matching and P be an augmenting path. Let n equal to m symmetric difference p. That means we have applied the augmenting path p on m. Then the vertices matched in m will remain matched in n. So the claim is basically, if m is a matching in p, matching and p be augmenting path, then and let n is the m symmetric difference p. That means we have applied the augmenting path on m, or applied the augmenting path p on m, and we obtain the matching n. Then we claim that the vertices that are matched in m will remain matched in n. Okay, and we can see it from the picture above. So this is the claim, and do you know how, I mean, how to prove it? The claim is, the proof of this claim is very easy. I mean, I think it should be obvious. Is it clear, the claim? Okay. So so from here we have seen that mj is obtained from mi after several augmentation. Okay, that means the vertices which are matched in mi remain matched in mj. So from here, so I'll just go to the next page then. uh, proof of our lemma. The vertices that are matched in mi remain matched in mj. Okay. Now, uh, and one more thing is that we remove, um, just a moment. So one more thing to notice is that since in g prime j, uh, the vertices of type oi and ui do not have edges of rank strictly greater than I incident to it. That means they remain matched to a edge of rank at most I. Into it, they remain matched to an edge of rank at most I. Okay, and that means edges of the so basically the in G prime J, in the graph G prime J, the vertices of type OI and EY do not have edges of rank I incident to it in graph G prime J. Why? Because these vertices were of type OI. That means during the ith iteration we have delete all the edges of rank I plus 1 or more incident to those vertices, right? So that's why those vertices cannot have any edge of rank greater than I in G prime J also. Okay. Okay, great. So now, so that means they have only have edges of rank at most I, and I have already showed that if an edge is matched in some graph, and we have applied some augmenting path on that particular graph, only augmenting paths, then those vertices will remain matched. So that means those vertices, the vertices of type OI and EY will remain matched in G prime J, and they will be matched to a edge of rank at most I. Okay. So what we can say from here, from this is, therefore MJ has at least as many edges of rank I as rank less or equal to I as mi. Is the claim, can anyone tell me how this claim is true? So from here we can claim that mj has at least as many edges of rank less than I, less or equal to I as mi. Can anyone tell me why it is true? Okay, so one thing is that in mi, the do you remember mi was a maximum matching in G prime I, right? And what is the size of a maximum matching? If you check the Galois decomposition, size of a maximum matching, max matching is odd plus u by 2, right? So the number of odd vertices and the number of unreachable vertices divided by 2. Now we have seen that the vertices of type oi and ui remain matched with an edge of rank less or equal to I in G prime J. That means the number size of the matching in the all the vertices that were matched with an edge of rank less or equal to I in, okay, no. So size of the matching in G prime I of mi was oi plus ui by 2. So it will be oi plus ui by 2. And we have seen that all the edges incident to oi in G prime J are of rank less or equal to I. And also all the edges of rank, all the edges incident to ui is also less or equal to I. So that means the number of matched edges, the number of edges of type of sorry, the number of edges of rank less than or equal to I in mj is at least oi plus ui by 2, because ui edges are incident to other ui edges and oi edges are, sorry, ui vertices are incident to other oi vertices and oi vertices are incident to and ei vertices. So from here we can claim that uh, therefore the number of mj has at least as many edges of rank less or equal to I as mi. And one more thing is mj cannot have more edges of rank I less or equal to I than mi. Yeah. Yeah, yeah, yes. Size of mi is equal to size of oi plus size of ui by 2. Now I'm saying and from each vertices in oi we get one edge in mj, yeah, rank at most I, and from each vertices of ui also you are getting one edge of rank less or equal to I. And ui vertices, those edges can be counted twice because ui goes to ui, and these edges will be counted once because y goes to ei. So that's why, yeah, yeah. Okay, thank you. I mean, this explanation was better, I think, with your help. Just one moment. And- okay, okay, now I think it's visible again. Okay, so okay, so this part is clear. Why mj has at least as many edges of rank less than I, less or equal to I as mi. So after that, uh, also one more thing is that mj can't have uh, more edges of rank I less or equal to I than mi. Why is it so? Because if mj has more edges of rank less or equal to I than mi, then we can just take the matching this mj intersection less or equal to I. So this particular set of edges, this matching will have more edges than mi. But mi is a maximum matching of G prime I. So it cannot be the case that mj has more edges of rank less or equal to I than mi, because then this will happen and it will be a contradiction, because mi is a maximum matching of G prime I, or mi is a mi is a maximum matching of G prime I. Yeah. So is it clear why mj and m? Okay, so from here we can claim that mj and mi have the same number of edges, same number of edges of rank less or equal to I. Okay, so basically this complete. Yeah, yeah, yes. Because we have already seen in the from the previous that the edges that we are removing, they cannot be part of any maximum matching of the rank maximal matching. Okay, so okay, don't think in rank terms of rank maximal matching here, because mj you are getting it from doing several augmentation from mi, right? So that's why this mj matching intersection of edges of rank less or equal to y, that set will be present in G prime I also. But mi, yeah, yeah. And mhm. Mm, yes, because we are not removing. We are not removing. No. That may not be the case, but uh, that may not be the case, but because we can remove some edges of like OI or OI of lower rank. Yeah, that's not the case. But here what we have is mj, we got a matching from mi by several augmentation. So uh, okay, just one moment. um, mj cannot have more edges. So mj will be a mj intersection this, it will be a matching in uh, G prime I. Will it be okay, this will be a matching in G prime I, because those edges, the edges that are matched in mj, those will be of type OE, not OO or OE, right? So those edges will not be removed from G prime J. Okay, I think this part I need to think it a little bit more and come up with a better explanation. Yeah, yeah, yeah. A superset. You want to say opposite. G prime I can, is bigger than I. Yeah, we have a bigger. Okay, so I'll come up. No, 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 no. But the thing is that the ages that are matched in MJ of rank less or equal to I, those will be uh, those will not be removed in. Okay, okay, okay. I think I got it. Those will not be removed in G prime I, because those edges are matched in G prime J. That means those edges were not removed during the iteration I to J, right? Yeah, at most. Okay, okay. Now I think I got the. Yeah, yeah, yeah. Okay, 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 okay. So I'll finish with this lemma and I'll prove the theorem and the popular. Okay, 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 okay. So see you. Bye. Okay, so now I think I got the explanation, proper explanation. Okay, so in MJ, the edges that are currently matched of rank less or equal to I, those edges are also present in G prime I, right? Because those, if those edges were removed during in G prime I, then those edges could not be present in G prime J. We are not adding any edge. Exactly. And that's why MJ intersection E prime E edges of less or equal to I should be a matching in G prime I. Yeah, yeah, because they cannot be added later again. If a removed edge cannot be added later. Okay, so that basically concludes that MI and MJ will have the same number of edges of rank less or equal to I. Okay, so this basically concludes the proof. So after that we have a theorem that basically, so I'll write down the statement of the theorem now. I'll prove it in the our final class, like after 2 weeks on 13th. So the statement of the theorem is, for every R, two things we want to prove. The second thing is, so in the main theorem we want to prove that every rank maximal matching of gk is a maximum matching of g prime k, and the moreover mk will be so if we the mk that we have computed, mk will be a maximum matching rank maximal matching of gk. So basically we are proving it both way around. So we are proving that every rank maximal matching will be a maximum matching of G prime K, and MK that was a maximum matching in G prime K will be also a rank maximal matching of GK. So this is like if and only if condition, and after and by proving this, we can claim that we will show we have shown that we will show that this the matching that we obtained from our algorithm is indeed a rank maximal matching if it holds for every iteration, if these two statements hold for every iteration from 1 to r. Okay, so we will do it in the next class. So is the statement of the theorem clear? So the first part says that the every rank maximal matching is a maximum matching of g prime, a rank maximal matching of g is a maximum matching of g prime, and the second thing says that maximum matching of G prime, that is MK, G prime K, that is MK, is also a rank maximal matching of GK. So it's like if and only if. I mean, it basically shows both ways. And if it happens, then I mean this holds for every rank maximal matching. Okay, so we are going to prove it in the next. Yeah. MK is the maximum matching of G prime K that we have seen before. Mm. Yeah, so it max sorry matching of G prime K. So this comes from so MK is a max matching of G prime K that comes from our algorithm and stuff. And previously we have assumed that. Yeah, so we are proving in the both way around. Like we are taking any rank maximal matching of GK, we show it is a maximum matching of G prime K, and we take any any maximum matching of G prime K, that is for now it, let's say it's MK. It will be a rank maximal matching of again GK. So it's like both way. That's the thing. Okay. So we'll see in the next class, and then I will prove this. Thank you.